Welcome Math 1040 students. This is a video recap of the lecture from Wednesday, June 5th, 2019. In class, we looked at section 9.1 on correlation and 9.2 on linear regression. We did so by looking at example 1 on page 491, and that actually continues. Example 1 is continued on to page 507 in section 9.2. That data set involved looking at the GDP of a country as well as their CO2 emissions for a particular year. So this first country had a GDP, an economic strength of $1.7 trillion. At the same time, they emitted 552.6 million metric tons of CO2. Right? And the next country, $1.2 trillion in GDP compared with a CO2 emission level of 462.3 million metric tons. So what we want to do is investigate whether there's a linear relationship between the X data, what we're calling the independent variable, and the Y data, the so-called dependent variable. One way to do this is to simply plot a graph of this data and see, does it look like a straight line or not. It doesn't have to be perfect. Correlation does not mean it has to be a perfect straight line, but it should fairly closely resemble a straight line. So let's see if that happens. Clicking cell C1, okay, we'll come to insert. Now normally we're using a histogram, but this time we're going to use what's called a scatter plot. This will just be a collection of dots in an XY graph that illustrates where these points fall. So this is in the third row, second column underneath the histogram selection. The first option is just scatter. I click that. Now Excel was nice enough to sort of intuit exactly which data we wanted to use to construct this plot, so it did it automatically for us. You can see it even put a title there. It did not include horizontal or vertical axis labels, but we know what those are. The horizontal axis is GDP in trillions of dollars, and the vertical axis is CO2 emissions in millions of metric tons. Now, in case Excel gave you just a blank graph, it didn't automatically do this for you. What you can do is go to our old friend select data. Okay, so maybe the chart data range for you is blank when you try to do that. That's okay. Just click on chart data range and select everything in columns A and B. Once you do that, you click OK, and you see I get the exact same graph that Excel made automatically for us. So that's done nicely. We can see, looking at this picture, that there does happen to be a fairly strong linear relationship in the data. We can see that this looks fairly close to a straight line. The way we measure that quantitatively, to actually assign a number, a numerical value to how strong that linear relationship is, was using the so-called correlation coefficient. The formula for that you can find on page 493. I encourage you to try and calculate the correlation coefficient for this data set by hand if you're feeling up to it. But I will warn you that it is a bit cumbersome. It does take some effort. So instead we're going to use Excel to do the heavy lifting for us. And it will make our life a lot easier. So remember, the variable letter that we use for the correlation coefficient is little r. So we'll just type in correlation coefficient so we don't forget what that small r value represents. And remember, Excel actually has this as a built-in function. So we can type equals CORR, and Excel says, okay, you must want to look at the correlation coefficient. That's exactly what it says. Returns the correlation coefficient between two data sets. So we'll hit tab. Array 1 are the X data values. So highlight everything in the A column, comma. Array 2 is everything in the B column, the CO2 emission data. Okay, once we have all that highlighted, we press Shift 0 to close the parentheses, hit enter, and we find that there's a correlation coefficient of 0.9116. So remember, the correlation coefficient satisfies the inequality that it must be greater than or equal to -1, but smaller than or equal to +1. The interpretation of that inequality was as follows. So if R was close to +1, that meant that the data strongly indicated there was a positive linear relationship. By positive, we mean the slope of the line that we would use to model this data goes up and to the right. And that's exactly what we see. So this is a number close to 1. and we see the data going up and to the right in a fairly linear fashion. If R was close to 0, that would indicate that there's really no relationship in the data, and what that would look like is just a bunch of blue dots kind of all over the screen. It wouldn't look like a line, it wouldn't look really like anything, just a bunch of blue dots. The other possibility was that R was close to -1. If R was close to -1, that would indicate that the data is still linearly correlated. Okay, it looks like a straight line, but instead this would mean that the slope was negative, meaning going down to the right. Okay, so those were the interpretations of the R value. Next, what we wanted to do, since we see that there is a strong correlation, strong linear correlation between the GDP of these countries and their CO2 emissions, was to actually plot the best fit line. So a line that maybe doesn't actually touch all these dots, but it's kind of the line that the dots are trying to be on, the line that they're trying to be close to or they're trying to be friends with. Okay, so we can do that by clicking on the graph. Okay, clicking on the graph, going to Chart Tools at the top and clicking Design. On the far left, there's a button that says Add Chart Element. We click that. Down towards the bottom, Trend Line, and then the second option is Linear. So that line that we have just placed on our graph is what is known as the linear regression line. This is, again, this is the line that the data is trying to basically sit on. It doesn't do it perfectly, but we can see it's fairly close. Now the other thing we discussed was how to obtain the equation for the linear regression line. So to write down the equation of a line, we know it's y equals mx plus b. So we need to calculate what the slope m and what the y-intercept variable b are. The formula for those two were as follows. The slope was given by r, the correlation coefficient, times the standard deviation, the sample standard deviation in the y data divided by the sample standard deviation in the x data. The y-intercept value, b, the formula for that is given by y bar minus mx bar. So as we talked about in class, these equations are not given in the book to my knowledge, but using them will make your life a lot easier than the equations that they do provide you in the textbook. So let's start with calculating our slope value. So again, to calculate m, we need to know r, the standard deviation of the y data, and the standard deviation of the x data. So we already know r. Let's calculate the sample standard deviation of the y data. So sy, and just again, we'll write down what this variable stands for. Y data sample standard deviation. Okay, so that's that. Okay, sx, same thing, x data sample standard deviation. Okay, and we can calculate these things. So this is a sampling of data. It's not a population set of data. It doesn't list every country in the world. So we're going to use our sample standard deviation statistic. Okay, so this is equal stdev. So we don't want .p, we want stdev.s for sample. Okay, press tab. So this is the sampling of the y data. Sy is the y data. So we'll highlight that, shift 0, enter. Okay, the standard deviation in the y data, 267.1644. We'll do the same thing, the sample standard deviation in the x data, stdev.s. Okay, shift 0. Standard deviation in the sample data, the x sample data is 1.4592. To calculate m, this is the slope of the regression line. Okay, again, that was r times sy divided by sx. So we simply type that in, equals. So we're going to take r times, now in parentheses, we're going to do sy divided by sx, close the parentheses, type enter, and that is the slope of the regression line. And if you look on page 507, you see they have the exact same value for the slope, 166.9004, and they carried a couple extra decimal points, but it's the same value. So that's one way of calculating the slope. Another is actually to use a built-in function to Excel. So we'll do this again just to show you that you get the same answer. So slope of regression line, say method 2. Okay. Another way you can do this is to simply type equals and then slope. So Excel has a slope function built in. It says returns the slope of the linear regression line through the given data points. That's exactly what we want. So we'll hit tab. So the first set of data it wants to know is the known y's, the known y values. So that is what's in column B. So we highlight that, comma. The next input the slope function wants are the known x values. So we highlight those, shift 0 to close the parenthesis, hit enter, and you see we get the exact same value for the slope. So however you want to do it is fine. You'll get the same answer either way. Okay, so we know the y value. What's next is to calculate our value for b, the y-intercept. And again, we need to know y bar, m, and x bar. Again, b is equal to y bar minus m times x bar. So we know m already. That's this value here. So we need to calculate our y bar. This is the mean of the y data. And we need to know x bar. So x bar, this is of course the mean of the x data. So we've done this a number of times throughout class. To calculate a mean using Excel, we type average, okay, tab, the average of the y values, okay, shift 0 to close, 526.3, and then x bar is the average of the x values. So we highlight that, shift 0, and enter. We get an x bar value of 2.46. So to calculate b, this is the regression line y-intercept. Again, the equation is y bar minus m times x bar. So we simply type that in Excel. So y bar, so equals y bar minus m times x bar equals 115.7249. Okay, if you look on page 507, compare that with the value they calculate for b, you will see we get the same thing. So all that's left is to write down what the actual equation for the regression line is. So regression line equation. So we'll just type this in by hand. We don't have to click on anything or use any built-in functions. This is y equals, so it's m, the m value, 166.9004 times x plus the b value, 115.7249. So there you have it. There's the combination of section 9.1 on correlation with 9.2 on linear regression. I hope this video was valuable. Thank you all for watching.